Welcome, Sonia.
Okay, so hi everyone, it's a pleasure to be here, and today I would like to introduce soft bioplastic structures that blur the boundaries between natural and artificial. These hybrids are capable of local interaction and have the potential not only to improve the immediate microclimate, but also to create new urban situations and spaces for coexistence. Based on the material they're made of, they serve as indicators of changes, from the microscopic and invisible to human eye to transformations of shapes, geometries, and spaces. So the idea is based on considering the biological materials as a valuable resource for retaining, absorbing, and emitting rainwater in the dense urban areas. This concept moves further away from the use of green roofs and permeable surfaces, which are applied in a flat and horizontal manner, toward realizing material and spatial speculations. Our research focuses on specific rice paper-based bioplastic. It's creating by applying solution onto the rice paper, which allows the material to be layered into various thicknesses and dimensions. This material not only has absorption qualities, but also unique properties like impermanence and fragility, which are often seen as weaknesses in conventional architecture materiality. However, our approach embraces these characteristics as opportunities to create responsive and adaptive spaces. Like living organisms, these materials exhibit an unpredicted behavior. In our approach, we try to adapt to these continual changes rather than control them rigidly. So we've developed 3 types of rice paper bioplastic: solid, foil, and foam foil. As you can see, each type has distinct properties like texture and transparency, absorption and evaporation, and also they interact and degrade differently. This makes them suitable for different positions within our intervention to urban and public spaces. We designed several experiments to gain a better understanding of the water absorption and evaporation dynamics of each type of the biomaterial and exploring the continuous interaction with immediate surroundings, temperature, humidity, and changes in surface morphology. So it's a versatile bioplastic that can collect and direct, absorb and release water while constantly changing its properties from soft and flexible to rigid based on environmental conditions. During the experiments, we also observed how the material transforms in time, and here you can see the changes of each type under the exposure to the natural conditions in exterior after 1 month. When the solid rice paper-based bioplastic absorbs the water, it expands and swells, creating folds and bulges that can serve as in-between spaces for another potential research of behavior or habitation. We treat bioplastic like textile membranes, forming spatial structure from flat sheet materials by cutting and sewing them together. The seams go beyond their usual function, acting as flexible ribs that shape the material and adapt to its natural changes. There are flexible boundaries allowing the material to shrink or fold in response to environmental factors. The funnel shape is not only spatially firm and solid, but it also effectively captures and guides water its designated destination. This design supports processes like evaporation and ventilation, reducing the risk of mold foldation. So individual funnels are sewn together in pairs, creating double funnel, which is in our concept the basic bioplastic module. It also defines the shape of the construction module made of glass fiber rods. This ensures that changes and modification remains localized within the module with the help of the high tensile strength of glass fiber rods, preserving the stability and coherence of the overall structure. This creates a synergy between the permanence and tension of glass fiber rods and the constantly changing biomaterial. The design consists of 3 scales of bioplastic funnels that form a modular system. The solid bioplastic has the best water absorption properties, and also that's because because of that it's used in the sponge-like parts of the structure that are made of the smallest bioplastic funnels. Also, the folds they form along with the material swelling can create potential habitats for small organisms. The foil bioplastic collects and distributes water because it's low weight and the lowest rate of shrinkage. It occupies the upper parts of the structure. The foam foil bioplastic effectively absorbs moisture from the surrounding and evaporates it at the slowest rate, thus helping to maintain a better microclimate. Interaction with other species are complex, so designing modern human spaces require making architecture more open to diversity and thus fostering interspecies cohabitation. These objectors should trigger new processes or connection without fixed outcomes, while also accepting the potential of unpredictability and even a failure. The verticality of the system predefines the heterogeneous characteristic inside the structure itself and allows us to control reaction toward the environments. Therefore, the material distribution over the module of the assembly codes its own temporality. This modular system can expand and contract, adapt to various settings, and even potentially provides habitats to small organisms. As ever-changing construction, it could fill voids in urban areas and cool them down, occupy facades, pass through squares, or penetrate brownfields, and blur the boundaries between conventional typologies. The bioplastic part of structure is integrated into an annual cycle. In spring, the construction is woven with biomaterial that retain rainwater during the hottest month and cools them down. Over time, it begins to transform and degrade until by winter, when the moisture retention is no longer needed, it naturally dissolves. The sponge creates a dialogue between control processes of fabrication and microprocesses of material transformation. Perceiving architecture as unstable, soft, changing, and vulnerable allows us to experience space in a state of constant creation and disappearance or care in individual stages. Okay, thank you.